This is going to be for Chem 102. This is section 10.8. So in this section, we're going to look at something that has to do with ionic compounds, which is a little bit maybe seemingly off topic, but we're going to talk about a process where we use enthalpies. So I want you to take a look at the difference in some of these properties between ionic and covalent compounds. And then we'll look at a reason why this is true. So ionic compounds, like sodium chloride, are more likely to be solid versus some covalent compounds may more likely to be liquid or gas. You see that there's a really high melting point for ionic compounds versus covalent. The heat of fusion, which is the amount of heat needed to melt the substance. We'll learn a little bit more about that, but to melt it, it takes this much energy. That's the enthalpy of fusion. For ionic compound, takes a lot more energy to melt than a covalent compound. You know this, right? Because you can melt sugar really easily, but you've never melted sodium chloride. You've never melted salt, at least not on your like stove. The boiling point is also way higher for ionic than covalent. The vaporization, molar heat of vaporization, is basically the enthalpy of evaporation. So the energy we have to put in to evaporate something, again, is really, really high. We see we have more solubility in water for ionic compounds. They're more dense. They don't really conduct electricity as a solid, but if you are able to get them into liquid or aqueous form, they're good conductors of electricity. Aqueous form is really easy because we just dissolve it in water. And then covalent compounds just don't conduct electricity very well at all in general, even when you try to dissolve them in water. So why is this? This is due to lattice energy. And lattice energy is defined in the next slide, but I'm going to go ahead and write it out here. So lattice energy is the energy needed to break apart 1 mole of an ionic compound into its ions in gas form. So if so for lattice energy, let's look, it would be, I don't know why they have this equation here. So for lattice energy equation, they have this other equation here, which is not the same. So lattice energy equation for sodium chloride would be take the solid sodium chloride, and what would be the enthalpy, the amount of energy you need to break it into its ions if the ions are in gas form. It's easy to break into ions in aqueous form because we would just dissolve it in water and then we would get ions aqueous, but we're talking about making the actual ions into gas. So the lattice energy is how much energy you need to do that reaction I wrote in blue. Now, that might be really difficult to measure, and that might be difficult to do exactly that reaction, right? Take something that's solid and then immediately break it into its ions and also make those ions gas. So what we can do is like Hess's law, where we can think about stepwise processes and then add all those enthalpies up to get the lattice energy. So hypothetical steps in the formation of these ions, and the ions can come, you can think about them also as coming from the elements as they exist. But the lattice energy technically is the energy you need to take the ionic solid and turn it into its elements. But it may be difficult to think about that. So let's think about just turning the elements into ions first. So first we would have to take our sodium and we'd have to turn it into gas because we want to change the phase to gas. What do we call it when we take solid and turn it into gas? Call this sublimation. Let's see if they call it sublimation here. They just call it the formation of the gas, but we can think about it like this sublimation. You may see the word atomization, meaning that you're atomizing it. Like if you spray like a perfume or something that goes through an atomizer, it like essentially tries to turn the liquid into a gas. So we can think about maybe those words, but you might know this process as sublimation a little bit easier. We can also think about it as the formation. So we can think about it as the enthalpy of formation of sodium gas. So we're forming the sodium gas specifically from sodium as it naturally exists, which is the element in its natural state of solid. Then we have to turn the chlorine, and chlorine naturally exists as Cl2, but we need to turn it into one chlorine, right? One Cl, because the ion doesn't have two chlorines bonded together. So we need to turn it into the atom. And so again, we'll talk about the enthalpy of formation of just one chlorine. And so we balance like a formation reaction, right? So 1 mole of product. So we got to balance the equation by putting the 1/2 in front of the element as it naturally exists. So think about it as formation reactions of the solid, of the gas form of each of these things. And we want single particles, right? Not like Cl2, because Cl2 minus is not the way that chlorine is as an ion. Chloride is just one chlorine. Then we need to make them ions. So we need to take once we have our sodium gas, we need to make it an ion, which means we got to remove an electron. What do we call it when we remove an electron? This is the ionization energy. Oh, I guess I can write it down here. They have it written down this way, but ionization energy. And this is the first ionization energy because it's the first electron we're removing. You can have second ionization energy where you have take this Na plus and we remove it again. Then we have to take our chlorine gas and we got to add an electron. This is the electron affinity. The electron affinity is basically how much energy do you get when we add an electron. So the way that the textbook is doing this, this one, the electron affinity, is that the change in enthalpy for the electron affinity is negative, but by definition, electron affinity is the amount of energy released. And so it's just amount of energy. So electron affinities you might see in the table as like just 349, right? But because now we're talking about enthalpy, we're talking about like a direction. If we know it's released, sorry, we might see it not as negative 349, but as regular 349 if you just look up electron affinity. But because we know energy is released during this process, it would be negative because it's exothermic. Ionization energy is positive because you have to put in energy. This one we get out the energy because we're making something more stable. Sometimes electron affinities can be positive because the element doesn't want an extra electron as much. So we have these processes, and we can think about these as chemical equations and then use Hess's law to rearrange these to get the equation that we want. So, this is called the Born-Haber cycle, and this is a process that we can use. It is basically just Hess's law, and it's a state function. So if we want to go from gas ions to solid sodium chloride, that's the lattice energy. We would go from our gas ions to our solid, that's the lattice energy. Or I guess the lattice energy is moving up, right? So it's different in different textbooks. So in this textbook, lattice energy is defined as taking the solid and turning it into the gas. So that's why they have the arrows moving up here. That's your lattice energy. But if I can't really easily do that, I need to know the difference between these two places. What I can do is I can do this stepwise. So I go and make all these steps over here, and then I get from here to here, just in a different route. So it's a state function. So exactly what we've been doing, but now we're applying it to like a real world process. And this is how we can find lattice energy of something. So for step one, we are going to take our sodium chloride and we are going to make turn it into 1 mole of sodium and a half a mole of chlorine. So basically it's the opposite of the formation of sodium chloride. So we think about the reaction here, it would be, if we think about it going down, that's the formation reaction. So sodium plus 1/2 chlorine makes sodium chloride. So it's a delta HF, the enthalpy of formation for sodium chloride. However, we're trying to go up. We want to take our sodium chloride and we want to turn it into the elements. So we're going to flip the equation just like we would with Hess's law. So we're going to flip it. Let me move this a little bit. If we flip it, we're going to say NaCl goes to Na plus 1/2 Cl2. And that's going to be the opposite of the enthalpy of formation. So I would flip the sign if I'm going up, it would be regular if I'm going down. So the delta H for the step one is negative of the enthalpy of formation because I'm trying to go from solid to elements. And the elements are still in their natural form. So this is solid, this is gas, and this is solid. And this is solid, and this is solid, and this is gas. So it's elements in their natural form, just like what we talked about with enthalpies of formation. Now we're going to take it into pieces. So first we're going to deal with the sodium. We're going to take the sodium metal. This is sodium solid, and we're going to turn it into sodium gas. So this is going to be the enthalpy of formation of sodium gas. And so we can just look at that enthalpy of formation, and that would be our change for that step. Notice that that step, the chlorine didn't change. We're doing it one at a time. Then we have our sodium gas already, but we want to change our chlorine into individual pieces. So we have our chlorine gas, and we're trying to turn it into chlorine pieces. We need to balance this, so we'll say 1/2. And so this is the enthalpy of formation of the chlorine gas. This one is the enthalpy of formation of sodium gas. Again, this is all kind of over here. If you look at the slide and you zoom in on it, it's showing you these reactions, but I want to write them directly over the picture so you can see what I'm talking about. Then we got to turn them into ions, right? So we're going to use, let's do one at a time. So this is going to be the ionization energy. And I'm going to say IE1. That's the first ionization energy for sodium. Oh, where's sodium? We'll just say sodium. It's a gas right now. So ionization energy is always you start in gas form. So this is sodium turning into sodium ions, and we lose an electron there, right? Because we want to become a positive ion or a cation. Now, we need to, and remember what we looked at in the table here, this next one is negative. So we're not going to be going up anymore in our Born-Haber cycle. So to make space, we just copy this and we paste it over here and we say, okay, now we have our sodium ions and our chlorine atoms. We need to make chlorine ions. And so we are going to go down now, and this is going to be the electron affinity for chlorine. So it's going to be chlorine gas adding an electron to turn into chlorine ion, which is also still a gas. So now at this point, we have our sodium ions that are gas, and now we have our chlorine ions that are gas. And then we have our whole process, because what we're trying to do is turn solid sodium chloride into gas ion versions of sodium and chlorine. And we just did that, right? But step by step. So take a look at this, read through it, zoom in on it, study this, and then let's look at this example. So we're going to use the Born-Haber cycle figure as a guide. We're going to do cesium chloride. We want to calculate the lattice energy. So how can we calculate this? We literally are going to add up all of these things and get our lattice energy, because adding up all these steps and then subtracting this step is going to give us this space here. So we're going to add up step 1, step 2, step 3, step 4, and then notice that we subtract step 5 because we're going down, it's negative. So literally we just put all these numbers in there in the calculator. They didn't give us the first one, enthalpy formation of they didn't, in this table, it's the negative enthalpy of formation is not there, so it's not exactly just all those in the table, but it's each step. So enthalpy of formation of, so this is going to be, let me just write out the steps for you here. So this one was the enthalpy of formation of, or the opposite of the enthalpy of formation of the sodium chloride, because we're going to break it apart, we're going to unform it. Then step 2 was the enthalpy of formation of sodium gas. So we're going to form the sodium gas. Then we are going to form the chlorine gas. Then we're going to do the ionization energy, the first ionization energy of sodium. We're going to ionize it. Then we're going to do the electron affinity for chlorine. We're going to ionize it, but by adding an electron. So this is subtract an electron for ionization energy, add an electron for electron affinity. We just add them all up, and now we get the lattice energy. So let's take this example and try this formula. So they're giving you the ionization energy, we're giving you the electron affinity, we're giving you the enthalpies of formation, and why don't you try, well, I'm showing you the solution. Why don't you try it? So pause and try this. See what you get. Remember, it's really just like Hess's law. You're just adding up these pieces, but maybe try out writing out the actual reaction so you can see how the Hess's law aspect of it works. We'll do this in class as well, but give it a try. And you can also just follow this formula if you want to. Okay, so hopefully you gave it a try. So we're going to take the enthalpy of formation of the cesium gas. So let's start with step 1. I don't know why they don't just start with step 1. So we're going to take our, let me make here, starting with step 1. Let's start with step 1. So first, we're going to take our cesium chloride, solid, and we're going to turn it into cesium just in its natural state, which would be solid, and chlorine in its natural state, which is Cl2. This is the opposite of the enthalpy of formation, because the enthalpy of formation would be the reverse, right? Enthalpy of formation would be Cs plus Cl2 makes CsCl2. So the opposite of enthalpy of formation, if the enthalpy of formation appears given to me as negative 443, the opposite would be positive 443 kilojoules per mole. Okay, then we're going to take our cesium and we're going to make it a gas. This is going to be the enthalpy of formation of cesium gas, which is given to us here. Enthalpy of formation of cesium gas is 76.50. And I'm just going to put a plus in front of it because it's already positive, and we don't need to flip it. We don't need to flip that equation. So I can go ahead and let me write this up here for you. Enthalpy of formation, just so you're very clear that we flipped this one. So we know the enthalpy of formation. They give us enthalpy of formation of cesium chlorides. So let's write that formula. I'm putting Cl2 for some reason. I don't know why I'm doing that, which means I need to do a 1/2 here. This is also a 2. So cesium would be a +1. That's why I'm doing that. So this enthalpy of formation is negative. Let me make some more space. Is negative 443.0. So we're going to flip it. And so we're going to flip it. So really we flipped that enthalpy of formation, right? Just Hess's law. Then, so we have our cesium as a gas. Now we need to make our chlorine as a gas, but we need to make it just Cl, not Cl2. So we're going to do Cl2, 1/2 Cl2 gas, turns into just regular Cl gas. This is the enthalpy of formation of just chlorine. If we look up here, we have enthalpy of formation of chlorine is 121.3. We don't have to change anything about it because it's already listed for us as is. Okay, then let's make ions. So let's take our cesium gas. We're going to lose an electron. This is the ionization energy. First ionization energy. And they give that to us as 376. If you want, you can keep those plus signs on there, because they are positive. And then we want to do the electron affinity. So if chlorine gains an electron to make chlorine gas. And technically it's the first electron affinity because it's the first ion we're adding, and that one's negative. We're going to make it negative. So the electron affinity itself is just a positive number because it's defined as the energy you get out. But we're going to make it negative. So electron affinity is defined as just the amount of energy. It's neither positive nor negative. It's just, or it's the amount of, you can't have a negative amount of energy, right? So electron affinity technically is a positive value because it can't be negative energy, but my delta H for the electron affinity is negative because it's energy that's released. Because energy released when we gain an electron for some elements like chlorine. If you're given if you're given this, and for some reason its electron affinity is not negative, we don't want to subtract it out, then you'll be told on the test. So, but the enthalpy of that step is negative. And the electron affinity is the energy you get. So how much energy do I get? 349. But because I get that much energy out, the process is negative because it's exothermic, because we're getting energy out. If we add all of this up, let's look at what we would get. So let's look at Hess's law. I have cesium solid cancels. I have 1/2 chlorine gas cancels. I have cesium gas cancels. I have chlorine gas cancels. Electrons cancel. What am I left with? I'm left with cesium chloride, solid, and cesium ion, gas, and chlorine ion, gas. And that is my lattice energy. So I can just add all of these numbers up. Of course, I don't want to add up this first one because I switched that one. Just add all these numbers up. And again, I don't want to add up this one because we're not flipping this. We're just understanding that when we're given electron affinity, it is inherently always a positive number, but we're going to assume that it is always going to be the energy lost, because we're making a more stable thing with this ion, right? Chlorine is unstable, goes to more stable, exothermic. So my lattice energy will just be all of these things added up. Just like Hess's law. So 443 plus 76.50 plus 121.3 plus 376 and then minus 349. And if we add all of that up, we should get 668 kilojoules per mole. So I know this seems really complicated, but we're going to practice it. I want you to practice it, and it's just an application of Hess's law, but you just need to know what lattice energy reaction is and what the formation reactions are you're going to be given information for, what is ionization energy and what is electron affinity, because you'll be given information like this. So you need to know, okay, what's the reaction for this? What's the reaction for this? What's the reaction for all these formations? And what is the reaction I'm looking for, which is the lattice energy reaction. And once you establish all those, you can just use Hess's law essentially and just add up all these numbers. Okay? Don't let it be more complicated than that. And remember that it's just an application of what you've already learned. So for chapter 10, here's a little summary of all the key points that we talked about. Let me know if you have any questions about any of this stuff. And yeah, we'll see you in class.